You are viewing one of 10 modules developed through a project funded by Geoscience BC focused on direct use geothermal resources in British Columbia. This follow-up project was carried out between August and December 2016. The project was executed by Tuyaterra GeoCorp. These modules were developed from the Direct Use Geothermal Resources Roadmap published by Geoscience BC in June 2016. They incorporate additional educational material that were developed as part of the current follow-up project. The voices you will hear narrating the module are myself, Catherine Hickson, and my colleague,
Juliana Proenza.
There are 10 modules in total, and those modules are all available. We are now focused on Module 4, which are the steps to development. Now, this module is an important module because it most closely follows the roadmap. So as part of the 2016 project that ended in May of 2016, a roadmap which was meant to be a guide, step-by-step guide for how you would go about developing a geothermal resource. So we've already covered what is geothermal. We've talked about the definitions and the capabilities of geothermal direct use projects. We're now going to focus on that particular aspect as well as the components. What do we need to do to actually put together a geothermal system or project? And then we're going to have a little bit more focus on the direct use. So what is geothermal energy? Again, I would suggest that you go back to Module 1, where we cover some of the basic ideas about geothermal energy, and that themes continue in Module 2, and obviously as well as Module 3. So here's just a quick review. We have to remember that geothermal energy is the heat from the earth. We are tapping naturally occurring geothermal fluid from deep down in the earth, and not necessarily so deep. A kilometer, 2 kilometers, or 3 kilometers are the typical depths for extraction of hot fluids to be used in geothermal applications. What's important is we need fluid, and that fluid is water. That water has to circulate through fractures. We have to have porosity in the rock, and we have to have heat. Depending on what the heat, we can either produce power or we can use the heat directly. So we have to remember that geothermal has been used for thousands of years. How? Well, simply hot springs. Hot springs or thermal areas have been used by people ever since they were discovered. So we have this very basic background use of geothermal energy, but now in the present day, we're able to take that energy and harness it for power generation or for specific use of the heat for things like heating of houses, heating of greenhouses, and make a different kind of use out of that geothermal energy. So what we need to understand, though, before we move into a project is, what do we actually have? What is the temperature of that resource? How much water is flowing through it? How much can we extract? We need to understand basically what's its chemistry. Is it benign, say neutral pH, or is it quite acidic? Because that will make a big difference in how this project is developed and goes forward. And also we need to take into consideration, what's our market? What are we going to use either this power for or this heat energy? So the other part and what we want to focus on is direct use projects. We've already touched upon power generation, and from the other modules, I think you'll find that power generation is much more costly. We need higher temperatures, and it's can be a much longer development process than direct use. So direct use is waters in British Columbia that are less than 80 degrees centigrade. So in fact, that that's just a cutoff that is related to regulations. Even water that's 65 or even 40 degrees centigrade water is very good for direct use. And we've got lots of applications. If it's wintertime and you're up in northern or central BC, snow melting might be a very appropriate way to use that thermal energy in your geothermal resource. So Juliana, why don't you take on from here?
So we're just going to go through some of the those details in terms of what is the amount of energy that you can use for a system, and what does that mean in just everyday life in terms of how you heat your home as the simplest method of using that heat. Some of the capabilities of low temperature waters in terms of the end use facilities, they can either be built near a thermal manifestation, and one of the concepts that was really important in the roadmap is the thermal manifestation, or the area of a geothermal resource. Within a short distance, about 8 kilometers was sort of the cutoff that was decided on, because anything greater than that would require higher costs for piping the resource to the end user. So heat supplied by thermal waters can substitute essentially any thermal energy that's currently derived from fossil fuels or electricity, as would be the case often in BC. The primary objective is usually to replace fossil fuel generated heat sources such as natural gas, propane, or diesel. And although natural gas prices are currently low, the volatility in future price and eventual increase in carbon taxes, for example, are definitely factors that need to be taken into account when evaluating a direct use project. Because the important thing here is that no additional fuel costs would be incurred once a direct use project is put into place, because the heat source is essentially coming from the ground, and if managed properly, it would be renewable. The market demand for plant end uses really needs to be identified at the beginning stages of project initiation, and we'll go through that in a bit more detail later on. But if you've got a resource and you don't necessarily have the market demand, that would be something that would have to be created and would incur additional costs. And so a project may not necessarily be economic unless there was interest in bringing entrepreneurship to the area or tourism to the area and adding more of a market demand than would be otherwise there. One of the other characteristics of direct use is that operating and maintenance expenses are low in comparison to conventional heating systems, and it provides many years of low-cost, environmentally beneficial operation. These decreased costs to the end users essentially translates to increased profits that can be invested back to the community in the form of increased local employment and increased quality of life. So we'll be going in a bit more detail on the permitting aspects of utilizing geothermal for direct use applications. But as Kathy mentioned, the BC Geothermal Resources Act regulates geothermal waters that are greater than 80 degrees Celsius. And these are only the subsurface rights, so you would still require to get the proper permits in place for land and water rights. And so essentially any resource that is greater than 80 degrees involves 3 major permitting bodies that you would have to go through in order to put your permits in place. For direct use, on the other hand, which ideally would be waters that are under 80 degrees Celsius, so that you are not regulated under the BC Geothermal Resources Act, again, you would still require the surface land and water rights. And so these are regulated under the Water Sustainability Act and the Land Act if the land is Crown land. So over the next couple of slides, I'm going to take you through an example of a calculation that is provided in the roadmap. And essentially what this calculation does is provides you a way to calculate what the available thermal energy would be if you knew the characteristics of a geothermal resource. So you would need to know things like flow rate and the difference in temperature. So at what temperature are you extracting the fluid of the geothermal resource, and at what temperature are you putting it back into the system? In this example, we've got a flow rate of 5 liters per second, which isn't very great, but it is not an insignificant amount and can definitely provide a lot of energy. And the important thing here is what is the difference in the temperature between extraction and reinjection. In this case, that difference in temperature is 40 degrees. And this calculation would come out to be the same whether or not you were looking at 60 degrees Celsius extraction and then reinjecting at 20 degrees, because that difference in temperature is still 40 degrees. So that's an important point to make there. And then what you've got here on the right-hand side is essentially just the units that are required to make this equation work in order to convert the units properly. So we've got 5 liters per second, difference in temperature that's 40 degrees Celsius. You've got the specific heat capacity of water, which essentially is just the amount of energy that is required in order to increase the temperature of water by 1 degree Celsius. So that's why you need this conversion factor, because you've got degrees in your difference in temperature, and then you've got time in there in order to give you the available energy per time, and then you've got the conversion factor in terms of how much mass you have in a volume of water. So using these different characteristics of a resource, that gives you about 3 million kilojoules per hour. But what does that really mean in terms of an end user? So again, what's a kilojoule? What is a kilojoule per hour? We can convert that to a more often used energy unit, which is kilowatt thermal. And so you've got the 3 million approximately kilojoules per hour, and then you're converting it to kilowatt thermal, you get approximately 800 kilowatts. And let's say in this case, the capacity factor is about 50%. So what that really means is that even though you've got this available thermal energy, due to various losses in equipment and distance to transport the fluid, you are losing a certain amount of heat. And in this case, we're assuming that that loss is 50%. So that takes your final thermal energy to 400 approximately kilowatts. So to put that into context, in terms of just a household energy usage, household energy usage is typically quoted in gigajoules. So again, there are very different types of energy units that are used, and what causes confusion is that different sources use different sources. So the Government of Canada uses gigajoules for household energy use, and there's approximately 1 million kilojoules in a gigajoule. So in this particular example, the amount of energy of this geothermal resource that's 5 liters per second and has a temperature difference of 40 degrees equates to about 13,000 gigajoules per year. And since household energy usage is often quoted in gigajoules, we know that the average household in BC uses about 100 gigajoules per year. And generally 80% of this energy is used for heating and hot water. So what that tells us is that in this example, this geothermal resource would provide enough energy for 165 households based on the average household energy usage. And hitting home that 80% of the household energy usage is for heating and hot water, you would be almost completely replacing the heating requirements of a home with a geothermal resource. So what are some of the examples of direct usage in BC? So as we've mentioned, spas and bathing is by far one of the most popular usages globally, and that is no exception in BC. So we've got about 10 hot springs in BC that are exploited commercially. We've also got a couple of in Alberta, one in the Yukon, and one all the way out in Saskatchewan. And so this really here is showing you the characteristics of that resource as a geothermal system. You've got the flow rates, you've got what the spring temperature is at the source of the spring waters, and then what the temperature of the waters are being used at for the actual commercial development. And so, you see differences in temperature anywhere from, let's say, 10 or 20 degrees there, and you've got flow rates between 1 to 30 liters per second. And using the example in the previous slides, you can see how that equates to the kilowatt thermal energy capacity of that resource. So these are the two maps that were provided as part of the project report earlier in 2016. And so we've got the heat flow map on the left-hand side, and then we've got on the right-hand side basically put in context to where the areas of higher heat flow are in terms of what the communities that were contacted are and where the hot springs are located in BC. So that what this really shows is what is the development potential for the most anomalous areas and how are they related to the nearby communities. This is showing where the location of the commercially exploited hot springs that we've just gone through. So you can see that for the most part, most hot springs in BC are in the southeast corner. We've got a couple of examples in the Lower Mainland, Harrison Hot Springs, and a few through the corridor between Harrison Hot Springs and Pemberton. That also extends into the Meager Volcanic Complex area, where there are several hot springs in that area as well. And then we've got some areas in the north and northwest that also have had exploitation of geothermal systems for spas and bathing. And that's Liard and Mount Layton, which is actually a resort that's currently closed. So what we're doing here is we're just comparing where are the heat flow areas in BC from the map that was provided in the report, and how does that compare to the different end-use applications that we've talked about. So here you've got a map on the right-hand side that's showing you where private land is, and this is really just representing where does population in BC get distributed. And so for the most part, you've got the eastern side of Vancouver Island and Lower Mainland through the valleys in the interior and the southeast portion, and then the northeast area of the Western Canada Sedimentary Basin. And this map basically confirms where these populations are the most dense. So in terms of farming and protected farmland in BC, there's a lot of overlap again between where population is. And so what we're trying to showcase here is, so you've got the heat flow areas, you've got the maps that show where people live, then you've also got the areas that we know are arable farmland. And so there's a lot of synergies that could be evaluated there in terms of the geothermal resource areas and how they could potentially be used for farming or dense areas in BC, or in this case for fish farming or aquaculture. One of the other end-use applications for geothermal resources in terms of direct use applications is utilizing it at operating mines and even selected exploration projects. So if you've got areas in BC where there is a long-term mining life of a mine, or areas that are being explored and there are exploration camps that are utilized year after year for maybe 10, 20 years, these areas could utilize geothermal resources with respect to direct use, if you know there's a geothermal resource nearby, or even Geo Exchange, which is using the shallow earth in order to provide heating for the exploration facilities of a exploration camp or for facilities of a mine. And there are also some really sophisticated ways that you can use, for example, tailings at operating mines that are producing heat because of the metals that are within the tailings, and a huge amount of the tailings are basically stockpiled in one area, and this can essentially be used as a heat source as well, in conjunction with direct use applications at operating mines. So we were taking a look at BC and what the geothermal development potential is in BC, and this map really shows you how that relates geographically and geologically to the western side of the United States. And the United States is definitely one of the global leaders of direct use applications. And what you've got here is a map showing examples of where space heating or district heating is used, where geothermal resources are used for industrial applications or greenhouses, aquaculture, spas and pools, agricultural drying, and they also use it for snow melting. And then you've also got these sites put into context with where power plants have been developed in the States. And what I really like about this map is that it shows you the geothermal resource in terms of temperature. Where is it above 100 degrees Celsius and where is it below 100 degrees Celsius? And so you can see the distribution of where these applications have been put in place and how it relates to the resource at depth. So I'm going to pass it over to Kathy now to talk about the different thermal water topics that we'll be talking about over the next few slides.
Yes, so we've been talking mostly about direct use, and that's where we're going to continue. But now we're going to get into a little bit more detail about how we actually harvest this heat energy. And what we're doing is we need to get that heat to the surface. Once it's on the surface, then it can be pumped around, and depending on what the application is, the pumps and piping will be engineered into homes, into businesses, greenhouses, or whatever the particular application is. But what is important are those drill holes. So we need to drill down and figure out what in fact is our temperature. How much fluid can we pump to the surface? And if you remember those calculations that Juliana went through, that's what's key. How much energy can we move to the surface and deploy into our geothermal applications? So chemistry is important, but and that has to do with the engineered surfacing like pipes and pumps, what's it going to do to it. But another very important thing is reinjection. So reinjection will keep our system going. So it is one of the most technically challenging parts of geothermal development is to get reinjection correct. And what I mean by that is we don't want to cool our upgoing fluid. We don't want to have a drop in pressure. So that reinjection is a very important part of what we're going to be doing. Now, we've already talked about the geothermal regulations in British Columbia being 80 degrees C. So above 80 degrees C, you're under the Geothermal Act, and that is a whole different permitting process than below 80 degrees C. Typically, 74 is what's considered to be economically usable for power generation. So you can, in a very narrow range, use, if you have a resource which is close to 80 degrees, it can be used for power generation. But we have to remember that these will be binary plants, so we're using that heat to boil a secondary fluid. So these are different kinds of applications or different kinds of development than sort of a typical flash power system. But there is one location in Chena Hot Springs up in Alaska where they can use temperatures at that 74, even a bit lower temperature than that. But what has been developed there is a very interesting system, and it's going to be the focus of one one of the direct use examples that we're going to be talking about. So again, it's all about temperature and flow rate. So as the calculations on the amount of energy that you can extract show, we need both the temperature of the fluid coming up, how are we going to, or how much of that temperature are we going to use, that energy that's in the fluid. And it's very important to understand that, because that really is how we're going to make our development. What can we do with that hot water? How much of it do we have? How quickly can we get it to the surface? And I've already mentioned about reinjection. So reinjection is not a problem from the point of pollution, for example, because essentially what you're bringing to the surface, you are putting back down into the subsurface. And natural waters, even though we think about rainwater as being very pure, by the time it has sat around in a geothermal system for a while, it has changed its chemistry significantly. What we see, and if you recall from our exploration module, when I was talking about the production of clays and the dissolution of rocks and minerals such as magnetite, all of that dissolution, the dissolving of those minerals, puts material into the water. So it changes the water chemistry significantly. And that change can have both an impact on our surface pumps and pipes, but it can also have an impact on how we re-inject that material back down into the subsurface. So, as I've already mentioned, natural waters are rarely pure, even though we think about them as being pure. And in fact, that's why we call them brines. And you'll often hear what we refer to, we talk about fluids, we talk about water, but we talk about brines. And that's because the water has been transformed in the geothermal system to a brine. So it has a lot of dissolved minerals in it that is not normal. And what these dissolved minerals do is they can cause corrosion. So if our water chemistry is quite acidic, think acid, think like vinegar, very strong vinegar, that acid can corrode our pumps and pipes and create big problems. Also, as we're moving these fluids around and we're changing their pressure and their temperature within the pipes, what you cause is the minerals will come out of solution and crystallize. So you can think about that glass of salt water. If you leave it on the counter for long enough, what you end up with is a bunch of crystals. Well, this is what happens within geothermal development systems, where we have a lot of pumps and pipes, as well as into our reinjection. So it's important to understand that chemistry very well, so that we know how to combat things like corrosion, as well as mineral scaling and buildup within our pumps. Now, the sustainability and interface with existing users is also very important. So those produced waters, and what we mean by that is that's the water that we're pumping up to the surface. We now need to push it back down into the subsurface. And as I've already mentioned, this is a very important part of the process. We need to maintain the pressure so that we can continue to produce fluid, but we can't have it too close so that we're cooling the system that we're already trying to tap, but we need to have it close enough that it's giving pressure support. So these are part of the engineering considerations that go into a development project. So Juliana, do you want to talk about heat pumps?
So we'll go through heat pumps very quickly here, because we have covered it in a bit more detail in modules 2 and 3. But essentially what we wanted to hit home here is that geothermal heat pumps, or Geo Exchange, or ground source heat pumps, there's various terms for it, can also be used for heating and cooling and hot water use at the residential, commercial, and district energy system scale. And so essentially what a Geo Exchange system is the simplest type of geothermal system. And for the most part, this geothermal resource at the shallow earth, maybe 5 to 10 meters deep if you're using horizontal loop configurations, or even if you're drilling into, say, 50 or 70 meters deep, this system is not directly utilizing fluids within the earth. So you're extracting the heat from the ground, and you're using a binary fluid that's usually a refrigerant. So this resource is essentially a ubiquitous energy source that's available pretty much anywhere in BC and most of Canada, and it can be used for cooling and heating. It does depend on the location in terms of how deep you might be able to go, or depending if you have restrictions in terms of the land area around your home or around the end-use applications. If it is a greenhouse, for example, if you don't have the area to use, then you might have to drill, which would mean that the system is a little bit more expensive. And what's really important about Geo Exchange is that it uses the ground as a constant temperature resource. So if it's about 10 or 15 degrees, that ground temperature is maintained at that 10 to 15 degrees range throughout the year. So the ground can essentially be used as a heat sink in the summer, where you're removing heat from your home and putting it into the ground, and then vice versa. In the winter, you're using it as a heat source, where you're extracting the heat from the ground and using it to heat your home and provide hot water, depending on your system. So Natural Resources Canada and the U.S. Environmental Protection Agency have both stated that Geo Exchange is the most energy efficient, environmentally beneficial, and cost-effective space conditioning system that is available on the market. And although there are all of these positives, what's really difficult about deploying these systems is that there is usually a higher upfront cost involved. So these systems are, for the most part, very economically favorable for new developments. For example, if you've got new condos being built or a new development in a community, they are usually very competitive with alternative heating systems. And for the most part, that's where the most systems have been deployed. There are examples of retrofitting, but in most cases, it's really too much of a cost to bear for the consumer at that point. So heat pump systems and Geo Exchange systems can utilize temperatures that are much lower than direct use applications. Heat pumps essentially assist a geothermal resource by raising the intake temperature through compression to more desirable levels by coupling with a working fluid and more favorable thermal properties. So basically you're using a refrigerant that has different thermal properties, a lower boiling point, and utilizing that desirable characteristics of that fluid. So there are examples of Geo Exchange systems that have been quite innovative that utilize, for example, warm wastewater, ocean water, or even hybrid systems with solar panels, for example, or other alternative technologies where Geo Exchange can be utilized together with these types of systems. So we've got here an example of a community, Drake Landing. It's a solar thermal community in Okotoks, Alberta. It's at about 1,000 meters elevation. It's a new subdivision of about 52 homes. And we've got pretty extreme temperatures there in the winter and pretty warm temperatures in the summer. And it's won an award because it essentially uses solar panels to collect the extra heat that you have in the summer, adding it to a borehole thermal storage system. So putting that heat into the ground in order to provide the additional heat that is needed in the winter at such a northern community. So what has really become evident in the U.S. and globally in terms of developing geothermal direct use projects is that you do need the full support of the community. You need a community champion. You need a strong leader that will guide the project through planning, the permitting, financing, and construction and operating stages. You need a person or a small team that will take charge and see the project to fruition Otherwise, there are going to be challenges, and if you don't have somebody that really believes that the project is the best alternative in terms of environmental impact, which is usually why these types of projects move forward, then it's a project that will not be developed. So the different components of a direct-use geothermal system is, again, how do you get the hot water from depth to the surface? And that component is typically referred to as a production facility. So it's typically a couple wells or several wells. There's pumps incorporated into those systems that are bringing the water to the surface. And then there's a mechanical system that includes a system of pipes, circulation pumps, heat exchangers, and different controls that essentially work to distribute the heat to the different spaces and processes that require the energy and the heat. And it could be several meters, or it could be a couple of kilometers, depending on the development. And then you've got the disposal system. So where are you disposing that system? For the most part, injection wells are used in order to maintain the pressure of a geothermal resource, for example, and to minimize environmental impacts. That you don't want to be necessarily storing the disposed fluids in a pond. So direct use geothermal system is not something that you just use for residential or commercial heating. It can be scaled up or down to include, for example, tourism, recreational pools. If you've got demand for independent craft brewing, it could be used for beer brewing, greenhouses, aquaculture, fish farming, and all of these different end-use applications can be used in a cascading manner. So you would first utilize your resource for the highest heat requirement, and then as you run the fluid through the system, you can utilize for the lower temperature requirements.
So here's the schematic which puts that all together. And this really is the way of the future, is when you have energy, that energy, if you have higher enough temperatures, you produce power, but you use every kilojoule of that energy in some type of process. And this is probably exemplified in Iceland with the company called HS Horka. And if you look at their plants, the Reykjanes and the Svartsengi plant, what they are, they're calling them a resource park. So they're using that hot water for a whole variety of different things, everything from fish farming to greenhouses. There's the Blue Lagoon. Some of you might, if you've been to Iceland, have been there. Anyway, that is all part of the concept, using all of the energy resource that's available for various applications. So now, how are we going to do this? How are we going to put all of this together? So what the roadmap does is it goes through the various steps to, right from the beginning, how do we get a project going? So one of the things is you need to understand what is it that you're trying to do? What is it that you think you have use of energy for? Do you have greenhouses? Do you have large residential, or do you have large commercial buildings in your jurisdiction? Or even lots of houses that may benefit from the reduction of greenhouse gases, as well as the costs by having direct use thermal heating of homes. So you need to do an inventory of your community. What's out there? What could you use this energy source for? And we've already stressed the importance of a community champion. You need to have the people in your community that are interested in doing this work. It's not just one person. That one person definitely is important. They need to be a leader, kind of leading the charge, pulling everybody along with them to make something happen in the community. So we've already gone through the calculations about how do we figure out how much energy that we have. So that's an important thing. What's the water flow and what are the temperatures? Then we need to think about, what other applications already functioning? Like, do we have a brewery out there that might need additional additional energy? So take an inventory. Look at what you are already doing in community that may be able to help through additional energy source. You then need to think about logistics. How far away is it? If we're talking about a resource that might be, say, 20 kilometers from the user, either the community or potential, say, greenhouse complex, how economical is it to pipe that resource from the point where we're getting it out of the ground in the wells to where we're actually going to use it? So those economic costs need to be considered in a holistic way. Where are we going to use this, and how can we use this energy in a way that will defer costs, reduce our greenhouse gases, and be a positive impact on the community? So once you've considered all of these various aspects, we're doing what's called a pre-feasibility study. So all of those things that we've talked about in points 1 to 7 need to be put together, and now we're getting down to the nitty-gritty. What do we do? What do we need to do? What do we need to build to make this system? We have to remember that not just are we pumping the material out of the ground, the water, the fluid, the brine, but we have to pump it back into the ground because of the environmental impacts. We need to maintain the pressure of our system and keep the system going for decades. So another thing, an important consideration is that what kind of local workforce do you have? If we look at the situation in Alberta, for example, within the oil and gas industry, there's many skilled professionals who are used to working in drilling, piping, but moving a different commodity, moving oil and gas. Can those people, are they in your community, and can they be now looked at as a resource for helping you in your development of your geothermal? Now, we have to also remember that we're going to need money for this. So as we move along the development process, so we've done a preliminary assessment, we've now looked at our pre-feasibility study, we now need to move into a feasibility study. We now need to think, what money do we need to make this happen? And when we're talking about all money, we have to take into account it's not just the people working on the projects. We're going to need insurance, we're going to need permitting, we're going to need some legal help. There are many inputs that need to be considered when we're putting together our financial model.
So as the project progresses, there's continual and concurrent evaluation of several different aspects. So these include permitting. So as the project is being developed, you may need to modify your permits, resubmit them, things like that. You also need to evaluate whether or not an environmental assessment may be required, and you really need to be involving the community at every step of the way of the development of the project. Is a community happy with how the project is being developed? What sort of market evaluation has been done? Have there been identified community end users as potential consumers of the direct use resource once the project is developed? So the next steps after this would be to go through the detailed exploration that we've already covered in Module 3, the road building, for example, the slim hole drilling, the decision to move forward, independent evaluation, and then the more expensive development aspects such as deep well drilling, the casing of the wells, the extraction and final commissioning of the plants. So we're not going to be going into too much detail here with these aspects because we have covered them in Module 3, but we will be talking a little bit about just some of the components and equipment that is used in order to extract the heat from the wells, essentially. So we've seen the slide in module 2, I believe, where we talked about the two different ways where you could be extracting heat. You could be extracting it directly by utilizing the fluid within the ground, within an aquifer or geothermal reservoir, and that fluid is pumped through a well and then used directly for an end-use applications. Or you could be using a closed-loop downhole heat exchanger. And so you're drilling a well, but then you're actually installing the heat exchanger within the well, and then a fluid is running through that heat exchanger, and that is where the heat is being transferred into, is the fluid that's circulating within that equipment component. And that's what is actually used to transfer the heat to the final end-use application.
So downhole pumps come in basically two varieties. One are called line shaft pumps, and the other are submersible pumps. What you have to remember in the choice of the pump is the diameter of your well is important, how much fluid you can draw out of that pump, out of that well with your pump, and you also have to remember that in fact you are you're moving water, so that pump needs to be able to handle the water flow, get it to the surface, and move it around for you. So in terms of the pumps, it really is dependent on the diameter of your well and the amount of fluid that you want to pump. So the other things that need to be taken into consideration is that your well needs to be straight. Sometimes if you put, you can see from the diagrams, for instance, the line shaft pump, this is a long, it's a series of mechanical parts, and your wells need to be straight in order for them to work effectively.
And then in terms of, we talked about the two different ways you could be extracting heat utilizing the fluid directly from a well, or you could be utilizing the heat indirectly by using a downhole heat exchanger, or DHE. And so this is a piece of equipment that would be installed within a well, and essentially what this allows you to do is that it could save you money in terms of you would not need to dispose of your well fluids because it's not an open system, and you're essentially only extracting heat from the well, not the actual fluid in the geothermal resource. And the exchanger comprises several pipes or tubes suspended in the well through which a secondary transfer or binary fluid is pumped. And that is the fluid that extracts the heat from the ground because it is allowed to circulate by natural convection and gains heat by conduction. So now that we have gone through the initial steps, as you move from the initiation stage all the way through to final plant commissioning, again, we're just providing all of the different examples of how you could use geothermal direct use for different end-use applications. Basically, any process that requires heat or hot or warm water can use a geothermal resource. So we will be providing a couple of examples. One is a brewery in Klamath Falls, and Gina Hot Springs utilizes a hot spring for bathing, but it's actually quite an innovative resort where they also use the resource for greenhouses, for an ice museum, and basically different types of end-use applications all in the same area, really maximizing their heat extraction and investment money into a very sound economic model.
And I think that's, on that note, what's important is that you broaden your perspective. And really, I underscore that geothermal is anything that needs heat or hot water or even warm water is applicable to a geothermal resource. So broaden your perspective in terms of the kinds of things within your community that could benefit from the use of warm water.
The restaurant got started by Del Azevedo and Lonnie Clement. Lonnie got a home brew kit for Christmas. Beer started tasting good. Started making beer in the garage at Lonnie's house. Took half the garage, turned it into a homemade brewery using sinks and just anything that they could put together.
A couple of great guys started this in their garage.
More people started buying it, or they gave it away. They hooked up with a distributor, had the foresight to start looking for a building.
We're standing here in the brew house. This is where it all begins. We make really great beer. We try to be as green as we can in doing so. Well, as far as I know, we are the only brewery that uses geothermal energy in the process.
So far, I think we are. A lot of people have looked around and no one has came up with another brewery that is using geothermal. Started right as a development stage of the business. We tapped into it. It's a cost-saving thing. Also is ran throughout all our heating system, dishwater. It provides all the hot water and everything.
That's really huge in the green community, and we like to promote that.
So back in this room is where the geothermal water comes in at roughly 150 to 170 degrees Fahrenheit. The geothermal energy is used in the mashing process. That's when you're combining your grain and hot water. It rests at that temperature while enzymes that are present in the malted barley convert starches to fermentable sugars. At the end of this conversion, it's pumped into the lauter tun, which has screens on the bottom, filters the liquid, which is called wort, and at that point it is boiled between an hour and 2 hours, and that's when the hops are added. Early hops will impart bitterness to the beer, whereas hops added late in the boil will add aromas, flavors. At this point, the wort is pitched with yeast and fermentation begins and will take roughly a week in one of these tanks. From grain to glass, roughly about 2 to 3 weeks.
Their philosophy, I think, was just two guys just making good beer.
The beer's great, it's excellent. You wouldn't expect that from a smaller community as this. We've never really been known as having any kind of a culture.
I get to do what I love for a living. I get paid for it. I get to drink my work. It's delicious.
This morning on Green Power Today, we're getting into some hot water. NBC's Lester Holt traveled to Alaska to see how geothermal energy is saving a popular resort thousands of dollars. And he joins us with that. Lester, good morning to you.
Matt, good morning to you. The Chena Hot Springs Resort sits miles away from the nearest power grid and for years depended on diesel-run generators. Well, the decision to switch to a clean, cheap, and renewable alternative was easy, but figuring out how to harness the hot springs that made it famous proved to be a challenge. And it's been one that's paid off handsomely.
Deep in the snow-covered Alaska wilderness, where it seems spring is always a latecomer, hope springs eternal at this steamy oasis. The natural hot springs an hour east of Fairbanks draw thousands from around the world to the Chena Hot Springs Resort, where the waters not only soothe travel-weary guests, but help heat the resort's buildings.
Hey, Rusty, you got a copy?
But still burdened with huge diesel fuel bills to generate power on the sprawling remote property, owner Bernie Carl, a man seemingly in perpetual motion, set his sights on finding a cheap and renewable energy source. The answer, he hoped, was bubbling right below his feet.
It was coming from the ground, so you knew it was hot, and you knew that if you drilled deeper, you were going to get hotter.
But at 165 degrees, well below boiling point, the water Bernie was drawing from this well was not hot enough to drive electricity-producing turbines, or at least that was the assumption. These hot springs were discovered just a little over a century ago, and word quickly got out of the warm and what some believed were healing waters. But the full potential of this water as a source of energy wasn't tapped until just a year and a half ago.
This is supplying electricity to the resort.
That's when Bernie got together with United Technologies to invent a system that would use that 165-degree water to heat up environmentally safe refrigerant that in turn would produce the necessary steam.
Now feel this.
Today, 2 of the revolutionary generators hum around the clock, providing electricity to the entire resort complex. including this greenhouse where the resort grows much of its own produce year-round.
The more that we get addicted to oil, the better it looks here. When I first bought this place, oil was like 76 cents a gallon. Now it's $3.59 with no tax on it. It was originally going to take us, 5 to 6 years to get our debt load paid back on doing this energy project. It looks like now it could be 4 years. If the price goes higher, maybe I'll do it in 3 years.
Alaska leads the country in the amount of geothermal resources, and yet this is the first time it's been used here to generate electricity.
I started moving hot water around. I mean, was that honestly that simple. It really was. I mean, but you see, people would miss that for all these years. They missed the obvious.
In the meantime, the hot water beneath the resort is also key to an equally revolutionary cooling system that has made the resort's ice museum a year-round attraction.
95 gallons a minute of hot water, 75 gallons a minute of cold water. We make 15 tons of refrigeration. First time in the history of man, it's a 3-pressure absorption chiller. And it's the first and only one.
Through all this, Bernie Carl has become both the hottest and coolest thing in the world of renewable energy.
And what they've done at Chena is being closely watched in Alaska's many remote villages that depend on expensive diesel fuel that has to be transported hundreds of miles. And so there's a push for those communities to harness their own renewable energy sources, whether it be geothermal, wind, turbines, or even tidal power, Matt.
That contraption he showed you, that system in the building, what did it cost to build?
It cost about $2 million. I mean, it was a heavy investment because, as I said, the water wasn't quite hot enough for this, but they said, well, there's got to be a way. They invested in it, and we think it's going to pay for itself in a matter of years.
Cool stuff, Lester. Thanks.